So let's talk about more general types of reflection this time around. Let's start with a spherical mirror, or a circular mirror, that is centered around a point, and I guess in this case it's actually a semicircle of a mirror that is centered around a point and has a radius r. And we're going to send rays in towards this mirror at very close or very, very shallow angles and see what happens to those rays. In a lot of the beginning ray tracing, to make the math easier, we are going to use what's called the paraxial approximation. We're going to only use paraxial rays, and what that means is that the angle that a ray makes from being a straight zero angle ray is very small. That essentially these angles are going to be less than 10 degrees. When these angles are so small, you can make the following approximations to make the math easier. The sine of some angle in radians is equal to the angle itself in radians. This is all in radians. The cosine of some small angle is equal to 1, and the tangent of some small angle is just equal to the sine of the angle over the cosine of the angle, which, as you can see from up here, is also equal to theta. With those paraxial approximations, let's take a look at this circular mirror and see what happens. So let's do a little bit of a blow up here. Let's change the color so that it's clear that this is the mirror. And we're going to send in a ray like so. And let's see, we will use a light gray to denote the radius. So the tangent, whoa, that's not right at all. Let's do that again. The radius would be here. In other words, the radius of a curvature is centered around this point. And because of that, when the ray reflects, it will actually be the original angle minus this angle made here in order to make the reflection. The way to think of that is that at the point of incidence right here, I guess it would be more like this, the mirror, you can just approximate the mirror as a flat mirror like this at this particular point. So if any ray came in at exactly a straight incidence, or what we call a normal incidence, then the light would get reflected straight back. Anything that is slightly deviated from that, the angles on either side would be equal to each other. You can safely ignore the curvature at all other points at this point. If you take these different triangles, you will be able to make a few relations off the bat. We'll call this theta 1, we'll call this theta 2, and we will call this one, with respect to the mirror itself, theta naught. And the different distances are as follows. We're going to call this one, this distance here, z2. Z is usually the variable you use for this dimension, the dimension that the rays are propagating in. It's also very important to usually assume in ray tracing that rays travel from left to right. I did not make this assumption when I was in college and came out with some really weird results. So it's very important to remember that most people assume left to right. This right here is just R, which means this is a little out of scale in the drawing, but we'll ignore that for now, because my work as an artistry is not why I'm here. And all of these have the same vertical distance. We'll just call that vertical distance here y. From these relations, remember, we are making the paraxial approximation, which means these angles are very small. And the reason we're doing that is to take these approximations here and relate them to this. So tangent is opposite over adjacent. So the tangent of this angle is y over z2. So tangent of theta 2 is equal to y over z2. But since we're making this approximation here, we can just say that this approximately equals theta 2. And likewise, we can say that y over... This is actually negative because the rays are normally propagating from left to right, and this r is actually propagating right to left. It's just a sign convention. It doesn't actually change anything, but it's important to write it this way so that you are in sync with all of the textbooks on this subject. You would get a minus sign difference, and here it's just y over z1 is theta 1. From here, you can probably see we're going to make an argument to write the next equation. No matter what angle you make to the mirror, even if it's straight into the mirror or at a very oblique angle, the two angles that are made follow this relation. The first angle plus the second angle is simply equal to 2 times the mirror angle made here. So this angle is shallower and this one is steeper, but the angle is always conserved around this point, meaning that these two always add up to twice this angle. The way to think of that is, let's say I sent a ray straight at the mirror along this path. Well, the ray coming in has this angle, and the ray coming out will be bounced straight back and will have the same angle, meaning that the first and second angles will just be twice the original. And that's actually true for all of them. So let's just take that for granted to continue. From here, we can replace these equations here into this one. So when we plug them in, we've got y over z1, y over z2, and 2 y over negative r. If you divide by y and all of this, 1 over z1 plus 1 over z2 equals 2 over minus r. And from here, we're going to work on focusing. And what I mean by that is, when you do ray tracing, one of the reasons you do it is to see how the system is going to focus or diverge rays. For instance, if you're trying to make some eyeglasses for somebody, if you do enough ray tracing and using focusing, you can determine what's going to happen to the eye and the eyeglasses when light comes in. And focusing, the idea is this. We say that the original ray comes from this distance. Well, in focusing, we're going to say that this ray comes from a very, very large distance. And then we want to see from what happens to that ray. That's basically the definition of focusing. What happens to very distant incoming rays. So we're going to use this equation to figure that out. we are going to say that the incoming ray was very distant, which means z1 is very close to infinity. So we're going to say that this quantity here, z1, is pretty much 1 over infinity, which is 0, which leaves us with 1 plus over z2 equals 2 over minus r, which shows you that when z1 is very, very large, z2 is fixed. In this case, it is minus r over 2. And so when z1 is very large, z2 in any system that you can trace like this becomes the focal length. The focal length of the system. And what that means is this. If you have our mirror here and you have a ray coming in from a very large distance, wherever that ray ends up along the axis of the system is called the focal length. If you look at this, this is essentially what we've just drawn. If you then take z2 equals f equals this, then you can rewrite this equation. This part of the equation can be rewritten using f. And you will come up with this relation here, 1 over f. And this is extremely important. This is called the imaging condition. And this turns out to be true for lenses, mirrors, what have you, anything that's curved, anything that has some kind of focus. The original distance from the original ray and the ray coming off of the system, its distance is related to the focal length in this way. This is where the image turns out. In this case, the image is at the focal length because z1 is so large. But if you have some lens set up, let's say you've got some ray that starts from here, has z1, and this is z2, to here, then knowing the focal length of the lens will tell you actually where z2 is, where the image of this light comes. So that is really the important takeaway from all this imaging condition right here, and the fact that we actually got it from a curved surface that reflects. It's also worth noting that when you have a spherical surface that reflects, this is the focal length for a curved circular mirror. This is the focal length for such a curved mirror like the one right here. And those are the two important takeaways from this particular lesson. By taking reflection of equal angles, and the fact that you're using the paraxial approximation, you are able to come away saying we have an imaging condition and we also have a particular focal length. If you do not use paraxial approximation and you use very steep angles, then you will find that this system does not behave perfectly and everything does not focus to a single point. What it actually does is it focuses onto an arc, and I will show the different focusing points. It generally arcs like this in its focus. So this ray would image here, this ray would image here, 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 and so on and so forth. And so you'd actually get a focusing line like this. That gets a little complicated, and that's one of the reasons why eyeglasses aren't perfect, because they are in reality non-paraxial. We'll eventually get to calculating those in future sessions, but it's very important to start with this to make the math easier. Because we made the math easier, we're able to come up with well-behaved relations like these. So these two are very important, and we'll continue to use them in subsequent lectures.